So hi everyone, my name is Ivana. I'm from the University of Technology in Vienna, and today I would like to talk about our paper, Divide and Conquer, a compositional approach to game-theoretic security. So I would like to start by giving you a very high-level idea of what game-theoretic security reasoning actually is. So in terms of blockchain technologies, what we mostly find in literature is work done on cryptographic security. And cryptographic security deals with questions like, for example, if I have a key, can a malicious person steal my key? So this is very important and absolutely necessary. However, it is not sufficient. In our setting, we would like to go a step further and also examine game-theoretic security. As you will see in my presentation, in our setting, we deal with questions that analyze the economic incentives behind user behavior. So, as we will see, we will differentiate between honest and malicious players, and then we will analyze how users' behavior can make them gain some rewards or how it can cause penalties for other users. So how is it done? Well, blockchain protocols or any other protocols are first translated into game-theoretic models, and on this slide we can see one small example. So this is called the market entry game, and as we can see, we have two players, M and E. M is a company that is about to enter the market, and E is a company that is already established. The players can take actions, so at the very beginning, M can either choose not to enter the market or enter the market. If M chooses not to enter the market, then we reach a leaf where we can find the utilities. So in this particular case, M will obtain a utility of 0, whereas the already established company will obtain the profit of the market P. In the other case, if M chooses to enter the market, then the already established company can either choose to ignore M, in which case they share the profit, or to start a price war, in which case they both lose some assets. It is important to mention that we have one honest behavior or intended scenario, and we always analyze a game-theoretic model with respect to this honest behavior. Okay, so once you've seen the models, you might ask yourselves, what are the properties that we want to analyze and ensure that they hold? Well, for this, we differentiate between three types of behavior. We have the honest players, which always act according to the protocol. We have the rational players, which might deviate if they're incentivized to do so. That is, if a deviation promises them a strictly greater utility. And last but not least, we have the Byzantine players, which are potentially malicious and can deviate at any point just to harm other players. Having these three types of behavior in mind, we want to ensure that two properties hold. The first one being incentive compatibility, meaning that the honest behavior is always rational. And the second one, Byzantine fault tolerance, meaning that the honest players are never harmed. A protocol is defined to be game-theoretically secure if and only if the honest behavior satisfies these two properties. So in a previous work, this has been automated as follows. On the left side, we have our game, constraints, honest behavior, and security properties, and all of these are translated into a large set of SMT constraints, which are then sent to the SMT solver. Depending on the output of the SMT solver, we can either decide that a protocol is secure, in which case we support strategy extraction, or that the protocol is not secure, in which case we can do precondition generation or counterexample generation. So this worked nice for protocols of smaller or medium sizes, but as you can imagine, protocols in real life can be quite large, which is why the previous approach encountered serious scalability issues. Motivated by this, we decided to employ compositionality techniques, and this is what our OOPSLA paper is about. So in our OOPSLA paper, in the compositional approach, we proceed with two levels of reasoning. The first level of reasoning is to stratify over the different players. So imagine we have a large protocol and we have our three players, Alice, Bob, and Eve. And what the previous approach did was basically analyze the model and try to find out whether the properties hold for all players at once. During our compositional approach, we proved that this is indeed equivalent to showing that the protocol is secure for the first player, Alice, and then also for Bob, and lastly, also for Eve. Each time we analyze a protocol from one fixed player, we assume that this fixed player is an honest player. Moreover, every time that we analyze a protocol for one fixed player, we perform a reasoning on a second level, which we call divide and conquer subtrees. I would like to illustrate how this works based on a very small example. So recall our market entry game that we had previously, and let's assume that the intended behavior is taking action E and then taking action I. Moreover, let's assume that we analyze this whole game in terms of Byzantine fault tolerance for the player M. So we proceed as follows. We ask ourselves two important questions. The first one is whether the player that has a turn is the same one that we analyze, and the second one, whether we are along the honest history. Depending on the answers of these questions, we then analyze only the subtrees that are relevant in the situation. So in this concrete situation, we see that we have M as a player, and this is the same player that we are analyzing the property for. So we have the assumption that this player is honest. Moreover, we are along the honest history, so there is an honest action available, which is why we know that this player will take this action, and then we can reduce the security of this larger game to the security of this smaller sub-game. So in this particular example, we do not need to analyze the subtree after n. And here it is just a leaf, but in practice it can be also a very large tree. Okay, so using these two levels of reasoning, our approach now looks as follows. We still have the same things on the left side, but now we have our player-wise iteration and the analysis of only the relevant subtrees, and we can still decide that a protocol is secure and extract strategies, this time in compositional manner, or we can decide that a protocol is not secure and generate preconditions and counter examples. So this gave us a sound and complete approach, which we also automated, and I would like to highlight some differences between the old framework, Checkmate, and the new one that we call Checkmate 2.0. So one interesting benchmark is tic-tac-toe, because for this benchmark, the old framework did not manage to terminate within 8 hours, so it was a timeout, and the new framework terminates in 42 seconds. In terms of SMT calls, the old framework had just one SMT call with one very big query which captured the aspect of the whole tree at one, whereas the new framework performs more than 10,000 SMT calls, however, with small, compact queries which do not impose a burden to the solver. In terms of evaluated nodes, the old framework analyzes, as expected, the whole tree and all nodes, whereas the new framework analyzes significantly less nodes. Another interesting benchmark is the three-player routing protocol from the Bitcoin Lightning Network. For this particular benchmark, the old framework needed about 50 minutes to extract all counterexamples, whereas the new framework does this in 5 minutes. Okay, so this gave us a nice scalability improvements. However, we wanted to push the compositionality aspect even further, and we introduced something that we call piecewise analysis. So for this one, imagine that we have a large real-world protocol, and as you can see here, we have some spots where we have S1, S3, S2, S3, S4, and so on. So these are, again, trees, or what we call subtrees, which are not on the image because they're pretty big and they did not even fit on the image. So let's look how they look. So this is S1, and it's, again, a pretty big tree. And what we now want to achieve is we want to analyze these subtrees independently. So we take S1, we want to analyze it independently as a standalone tree. We want to do this with S2, S3, S4, and all the other subtrees that we want to extract. And once we do that, we extract only the relevant information from the result. Once we have the extracted relevant information, we can plug this in the supertree whenever these subtrees occur, and we can discard the subtrees themselves. Now we can analyze the supertree where some results have already been pre-computed. This is especially beneficial for a benchmark called four-player routing. So this is basically the same one as the three-player routing from the Bitcoin Lightning Network with just one more additional player. And this approach is important for this benchmark because this benchmark has been generated and analyzed for the first time. So previously, the generation exceeded the allocated disk space, and since we were not even able to generate it, we were also not able to analyze it. We now proceed as follows. We still run our generation script. However, whenever we generate one particular unit of the protocol, called the unlocking phase, we generate this as a subtree. We send this to our framework Checkmate 2.0, and then it is analyzed, so that just this subtree, and Checkmate gives us the extracted relevant information, which we then plug in to the supertree. After we have the relevant information extracted from the result of the analysis, we can discard the subtree itself, and as you can imagine, the extracted information is way smaller than the subtree itself. We do this quite a lot of times, and in fact more than 1,400 times, and in this manner we are now able to generate this benchmark, and since it is relatively small, we can also analyze it quite quickly. Okay, so in conclusion, when it comes to game-theoretic security, we've achieved significant scalability gains enabled by compositional reasoning, and we did this in several different ways. We had the player-dependent notions, which we referred to as level 1 reasoning. Then we had reasoning over subgames and analysis of only the relevant subtrees, which we referred to as level 2 reasoning. Then we saw that we had interleaved subgame and supergame reasoning, which was beneficial, especially for the 4-player routing. And last but not least, we now perform strategies and counterexamples generation in a compositional manner. Yes, so with that being said, thank you for your attention, and I'm looking forward to your questions.
Hello. Hi.
Hi.
I'm Anna. Good job. I was just curious, you said in part, I might have missed something, but when you said like the subtrees, you extracted the relevant aspects of it, how do you like decide what's the relevant aspects for a specific subtree?
Yes, exactly. So this is also one of the main contributions of the paper itself, because the naive approach would be to basically just extract whether a property is satisfied or not. However, this approach is unsound, and there are quite a lot of counterexamples. So for each property we have, so this is the contribution of the paper. For example, we have to extract for which players the property is satisfied or not, for which cases it is satisfied, what are the practical utilities or not. So it really depends on the setting and the property that we are verifying.
Thank you.
Any other questions? So I have a quick question.
Yeah.
Maybe, so you decompose your problems into smaller bits that are much more easy to verify independently. But is there a case where you decompose too much the problem and it becomes too small, and at the end of the day you're doing maybe slower because the granularity is too small?
So I think it really depends on the benchmark. So generally the new approach outperforms the old approach. However, there are some benchmarks where the structure of the benchmarks is way different than the others. So here it might be less efficient, but generally it performs better because the queries for the SMT solver become quite smaller and they're easier to handle for the solver.